Hello again, welcome back everyone to ptet.chemistry channel. So this is the second part of the VSEPR series, where in the first video I outlined what VSEPR was, and then I also talk about the importance of just counting the sigma as the bonding pair of electrons when we deal with VSEPR. So the difference between sigma and pi bond is something you should be familiar with already. If not, then I suggest you to think back about what is a sigma and what is a pi bond. Basically, in a double bond, you have one sigma maximum, and there will be one pi. And when I say maximum, that means between the two atoms, you can just have one sigma maximum, and the other must be a pi bond. Okay, so typically sigma and pi bond will have been covered towards the end of covalent bond, but some teachers will have covered it earlier because they are kind of prerequisite to understanding VSEPR. And if they are not, eventually when you cover it, you should be well equipped with all the necessary knowledge to work out how many sigma bond you have, and therefore how many bonding pair of electrons do you have around the central atom. So we talk about all the simple cases where there are no lone pairs, and therefore all the bonding pair will repel equally, like this 2 bond pair and 0 lone pair. We talk about cases where there was 3 bond pair repelling equally with no lone pair, and you have to specify by counting the number of bond pair. You have to specify the number of lone pairs by counting correctly and thinking about their number of outer shell electrons around the central atom. We don't use the dot and cross because they would be so troublesome and time wasting. We work out from our display formula where we just show the covalent bond as single lines. Single line represent 1 covalent bond. Double lines like this represent 2 covalent bond, of which 1 sigma and 1 pi. And you only count the sigma for the bonding pair of electrons. So we not only look at the single bond, we look at things like SO3, which is an important thing in O level and A level. You did it in contact process on your way to getting sulfuric acid. That also applies to molecules like in organic chemistry, you have alkene. And then you can also imagine that if you have, instead of carbon there, if you have like oxygen, there will be a different functional group. It's still going to be a trigonal planar carbon there, because it's all about counting the number of bond pair and the number of lone pairs. And if these are true, then the 3 bond pair repel equally. It was also true when you have ions. Ions can have ionic bonding between the cation and anion, between the negative charge ion and the positive charge ions. But within this carbonate anion, CO3 2-, commonly used to test for acid, because it will effervescence to give you CO2. You can also have this within the ion. You can have covalent bond where you can apply VSEPR to the central carbon and work it out to be trigonal planar as well. We then move on to this most important class, which is tetrahedral, where I say most important because there's a lot of it in organic chemistry. We need to know the bond angle, the shape, the 3-dimensional, how to draw them. That also apply to ions as well, such as this unusual MnO4-, which you typically wouldn't do in school, but I'm just outlining that just like we could apply it to a CO3 2- ion, we could apply it to MnO4- ion as well. Moving to more complicated examples, these are your case study in your period 3 chemistry, which involve group 15 chlorides like PCl5. So it's like a linear combination of a trigonal planar and the linear geometry in such a way that you get this trigonal bipyramidal geometry where the 5 bonding pairs are distributed in such a way that 2 of them are totally apart by 180 degrees, but the other 3 are best served by adopting a trigonal planar geometry, which was already optimized for the trigonal planar geometry, such that you get 2 bond angles and you need to know which one is which one. Obviously, the one in the equatorial plane follows that trigonal planar, whereas the one in the axial plane will not be 180 degrees. This and this will be 180 degrees apart, but now you have a central bisecting atom and a bond. That's why it becomes 90 degrees apart. This SF6 is a very common example where you have a group 16 element with single covalent bond, 6 sigma therefore. Then you get 6 bonding pair repelling equally, giving you octahedral, which is 90 degrees. So that was just a brief summary of what we covered previously. The next example we're going to cover involve introducing lone pair. Okay, so we are going to talk about systems that have lone pair of electrons, and maybe I can use a new page. So introducing lone pair of electron. When you have lone pair of electrons, you have 2 electrons because these are pair. Lone pair of electrons would mean they are non-bonding. Okay, some books will say it's non-bonding, not involved in bonding. Okay, so let's start off easy by talking about one lone pair. Okay, I use acronym, but you should use the full word. Yeah, lone pair of electrons. Okay, when you have one lone pair of electrons, and then we talk about shape because we need to have at least two bond pair of electrons. When you have a central atom, let's say M, you have a lone pair, and then you only have one. You only have one atom to which is bonded to. So there will just be one bond pair. You cannot have a bond angle between two atoms. Angle is always between three sides, right? You must have 3 points. You must have another point there, which means you must have at least two bond pair. Okay, so that's why I started with two bond pair, because to have a bond angle, you need at least two bond pair. All right, what does one lone pair and two bond pair looks like? You might not cover this specifically when you first cover VSEPR, but I assure you, you have seen this before. SO2. Yeah, sulfur is a group 16, or you will call it group 6, so it's got 6 valence electrons. It uses 1, 2, 3, 4 for bonding, because oxygen form double bond there. Okay, so there is 1 sigma plus 1 pi. There's 1 sigma plus 1 pi. So the number of bond pair of electron is only 2. But how many lone pairs are there? Just because I haven't drawn them out doesn't mean it's not there. That's why you have to do the exercise yourself. Group 16, 6 valence electron, uses 1, 2, 3, 4. Uses 4 out of 6 for bonding. You actually have 2 electrons left, and 2 electrons which are not used for bonding is 1 lone pair. Now your explanation is going to be slightly different, because VSEPR states that bonding pair electrons repel lesser than bonding pair lone pair repel lesser, which in turn repel lesser than lone pair electron. Is that true? Why is that true? Well, your bonding pair of electrons is between two atoms. So your bonding pair of electron is clouded by the atom size. Lone pair, not involved in bonding, naked, totally available. That's why, because they're totally available, they are not shrouded by any of the atomic size at all. When they are available, they can repel more between the bond pair and the lone pair compared to between the bond pair and bond pair, which are in between the atoms already. Okay, that's why this is an important statement. You don't write this down like this because no one will understand your acronym. You have to fill it out in words. So this is how the understanding works. Yeah, in terms of how available the lone pair is in space compared with how available the bonding pair of electron is in space. Yeah. So based on that, we say that the lone pair in words, okay, the lone pair bond pair will repel more than the bonding pair. Previously, if you have 0 lone pair and 2 bond pair, you will get linear, like CO2. But here you have 1 lone pair, and you can think about if this is like SO3. SO3 previously was 120 degree because it's got 3 bond pair, because it's got 3 sigma, 1 sigma, 2 sigma, 3 sigma. You only count the sigma. The sulfur uses all the 6 electrons for forming covalent bond. This is trigonal planar. But here it has lost actually one of the bond pair, and it's now a lone pair. Okay, and this geometry is called band. Okay, there's actually another geometry which is called band, but this band has got 2 bond pair and 1 lone pair, and surprisingly it's 120 degree as well, same as that. Okay, it's just determined by experiments. Okay, and most results of this kind of geometry with 2 bond pair and 1 lone pair, we state about the repulsion based on VSEPR, and it still give you band geometry and 120 degree. So that is actually 120 degree. Okay, so there aren't many examples of these particular combinations in A-level chemistry, but SO2 is the perfect example of something you have covered and something that could be asked together with contact process equilibrium, something that could be asked in terms of Kp calculation, something that could be asked in terms of dot and cross, etc. Yeah. So that was number 5. So let's talk about number 6. So there aren't many examples in A-level at all that are like that. Okay. So we go next to the more complicated example, such as 2 lone pair and 2 bond pair. Now this is a very common example in A-level because you have water, which is the classic example. Okay, water is a group 16 element, just like sulfur. So 6 valence electrons. You can call it group 6 or group 16. If group 6, you have to use Roman numeral. I'm using the numerical value here. So it's group 16 from my periodic table. There will be 2 lone pair. So based on this, just now, I have only used lone pair, bond pair. Why didn't I say this? Well, you only have 1 lone pair. When you only have 1 lone pair, how can you have lone pair repulsion? You only have 1, okay? That's why you need to count, all right? So the number of bond pair here is going to be 2 because there are 2 sigma bond, okay? The number of lone pair of electron is going to be 2 because you only use 2 out of the 6 for bonding. You have 4 more non-bonding electron, which is 2 lone pairs. So now we have to talk about the lone pair repels more than the bond pair lone pair. So now you have 2 pairs of non-bonding electron. They will repel more compared to this and this, this and this, which is the bond pair lone pair, which in turn repels more than the bond pair. If I draw it out in colors, so this is the lone pair. It repels more than bond pair, lone pair. Okay, so that is your green color, lone pair, bond pair. And then the one that repel the least, you can imagine it being bond pair. Okay, so I've tried my best to draw this on a bigger scale because this is the stronger repulsion than this, which in turn is stronger than that. So it's gonna flip the molecule further in. Okay, that's why the shape is even more bent, or some books will call it non-linear. I like the word bent. I love bent. Okay, but I know also the difference between the two bent. Okay, because this was 120 degree because there was only 1 lone pair bond pair repulsion. Here you have lone pair repulsion, which is stronger than bond pair lone pair repulsion. So your angle is going to be lower, much lower than 120 degree. It's actually 104 degree. Some books will say 104.5, whichever one you prefer, that will be close to the actual value. All right. Water is also similar to like H2S, for example. It's also similar to like HCl, for example. Okay, we are all talking about similar kind of chemistry. You can also think about SeCl. So selenium is below oxygen and sulfur. So they all will have similar kind of chemistry based on the electronic property of the elements in the same group, having the same number of outer shell electrons. All right. So number 8 is going to be slightly more complicated. If we have 2 lone pair, no, do I want to go that complicated? I know where I've gone wrong. Okay, I should have gone 1 lone pair and 3 bond pair first. So I should have stuck with 1 lone pair and 3 bond pair. Okay. Anyway, I'll go through it now. It doesn't matter. So there will be a case of ammonia. Ammonia, again, I'll draw in 3-dimensional because essentially that is how it looks like. You can think about the alkane or the CH4 just now being tetrahedral, 4 bond pair and 0 lone pair previously. Think about without that bond pair of electron, what are you going to have without that lone pair of electrons? So without this bond pair electrons, you're going to have a lone pair in substitution. Here you have 4 bond pair repel equally. Remember previously, 4 bond pair repel equally because they are not lone pair. But here you have 3 bond pair and you have 1 lone pair. Okay, so what's going to happen is you're going to talk about bond pair lone pair repels more than the bond pair. So I could show with this kind of arrow again, but I'm not going to do it here. But essentially you can think about the green kind of arrow. Lone pair, bond pair repel more than the red arrow between the bond pair and bond pair. Okay, but as you can imagine, here you have a lone pair repulsion, Whereas here you only have a lone pair bond pair repulsion. So you got to use your terminology carefully. What do you have actually and what do you not have? You cannot write something which you do not have. All right, that's the most common mistake. This is going to give you a trigonal pyramidal geometry. It's like a distorted tetrahedral. A tetrahedral is a perfect 109 or 109 degree where they repel equally in space, but you have to shrink it further down because now this is a lone pair. They push it down, so they push it down further. So essentially what happened now is your bond angle is slightly lesser, 107. And when you have two lone pair, when you take away the bond pair, when you have two lone pair, then it's going to look bent, just like that. Okay? So the angle progressively decreased from 109 to 107 to 104 as you progressively increases the number of lone pair, and you progressively increasing the extent of lone pair repulsion as well as the bond pair lone pair repulsion. All right. So those are the common case studies. I mean, the most common in A level really is CH4 versus NH3 versus H2O. Okay. But I'll move further to talk a little bit about more advanced concept that is to do with two lone pair. I already talked about two lone pair and two bond pair. That was with H2O example. I'm going to talk a little bit about two lone pair and three bond pair. Wait, hang on. Do you want to talk about that? No, not yet. There's one more example I want to show you. One lone pair and four bond pair. Okay, this is not in every single A-level syllabus. However, when they ask you, what is it? Sf4. Okay, this is something that will trick a lot of people. Yeah, the Sf4 geometry is actually looking like this. It is what we call a seesaw. It's like a seesaw. You could also imagine it looking. If you have played a seesaw before, you know that it will need a support in the middle, and then yeah. So both of these are similar geometry. So they have a lone pair there. Okay, so the lone pair is residing there. This is what we call a seesaw geometry. Okay, this is actually going to be 90 degree, but the one in between is going to be 120 degree. Okay, so there are two bond angle there, just like trigonal bipyramidal, which reminds you of something. I hope it reminds you of something. You can combine a linear geometry such as this. That was your linear, and then you could combine the one which was already like that, which was the bend, but it's the bend 120 degree. Okay, like for SO2 earlier. Okay, so you will have the number of bond pair and the number of lone pair. There you have two because you have two sigma bond and one lone pair there. Here you have two bond pair and zero lone pair. And then when you combine them together, you are going to get this thing which we call T-shape. Sorry, not T-shape, seesaw shape, okay? So I'm moving on to slightly more advanced style, which you might or might not cover in A-level, so you can skip it totally if you want to. But guess what? 4 bond pair, 1 lone pair. That is your seesaw geometry. Earlier, I think in the previous video, I showed you that you could combine a totally trigonal planar with a linear, and you will get trigonal bipyramidal. Okay, such as here, trigonal planar plus linear give you trigonal bipyramidal, and you get a 5 bond pair and 0 lone pair. I get this one with 1 lone pair and 2 bond pair from something I just covered in this video, which was on SO2. Yeah, but this is a bend 120 degree despite the lone pair bond pair repulsion. And over I give you this seesaw geometry, which retain the 120 degree there and the 90 degree as a result of you having the bonds in between the linear geometry now. Okay, so that's not too complicated there. Something which is more complicated will be this 2 lone pair, 3 bond pair. Okay, this is going to look like this. No, it's not going to look like that. It's going to look like this, okay? It's what we call the T-shape geometry. I hope you can see the T-shape. Where is the lone pair then? Well, the lone pair is there and there. Okay? So what have I done there? What have I done there? What I have done is, do I have an example here? No, I don't have an example there. Okay, this is something that's quite hard to explain. This is very common in what we call interhalogen. Inter means between. Interhalogen means between halogens. Okay, so interhalogens are well known to be T-shaped, and we are looking at a halogen which is like AB3. What does it mean? Where A and B are not elements, yeah? Where A and B are not elements. So we could be looking at things like BRF3. We could be looking at ICL3, etc., etc. These are molecules, by the way, okay? So although we usually associate halogen forming single covalent bond, you should be aware that, you know, halogen can form multiple bond as well, as it can form more than single covalent bond, which leave you 4 electrons which are not used for bonding, because you use 1, 2, 3 for bonding. There are 4 more. So that gives you 3 sigma bond, 3 bond pair, and 2 lone pair. And that will give you the 90 degree there. Okay, we don't talk about the bond angle between there and there because these are just lone pair, but that will give you the 90 degree T-shape. So something you might not be familiar with unless you are specifically doing this for your A-level curriculum, yeah? The last one that I'll talk about really, it's about 2 lone pair and 4 bond pair. This one is quite interesting. It's to do with the chemistry of noble gases. Okay, so I've only seen it so far with xenon. So you know where xenon is, right? So xenon is a noble gas. So they do react. They give you this thing called Xef4. This is Xenon Tetrafluoride. So xenon is a group 18 or noble gas element. It's got 8 outer shell electrons to be used for bonding. If it does form a bond, 1, 2, 3, 4, it used 4 for bonding. It still has 4 more. So that is your 4 sigma bond. That is your 2 lone pair. The lone pairs like to repel as much as possible. Here they are 180 degrees apart. That is the maximum distance they are far apart, and that's why it gives you a square planar in the middle. Okay, so that's 90 degrees. That gives you a square planar geometry right in the middle. Okay, so which means I have not drawn it perfectly, but I could have drawn it like this. It is flat. Where there is 90 degree, that is also 90 degree. All of the bond angle is 90 degree. I've just drawn it 3-dimensional like this, but there is going to be 90 degree as well. Okay, so that's the end of this second part of this VSEPR video. In this video, I cover the concept that involve the lone pair repulsion, whereas in the previous video, it was much more simple without the lone pair repulsion. We started off nice and simple with 1 lone pair and 2 bond pair. It's your SO2, which is quite common in your A-level as well as O-level. And this is a different kind of band, 120 degree, as compared to this band geometry where you have 2 lone pair and 2 bond pair, because the lone pair can repel more than bond pair lone pair, which in turn repels more than bond pair. In here, where we only have 1 lone pair, we do not have this. That's why I do not explain this in here. But here we have more than 1 lone pair. When we count the number of electrons carefully, we can work out the number of lone pair correctly. Lone pair is pair of electrons which are not used for bonding. It's a pair. So 2 lone pair refer to 4 electrons that are not used for bonding. I've got to talk about VSEPR because to get the shape, to explain the shape, okay, to explain geometry and shape, I have to use valence shell electron pair repulsion. It's called electron pair repulsion theory for a reason. It's not just counting that. It's not just stating that. It's to do with the repulsion theory, which you need to explain. Yeah. Ammonia is something I should have done in between, because there's the intermediate in between 4 bond pair, 0 lone pair. Take away a bond pair, introduce a lone pair. I will have a little bit repulsion between the lone pair and the bond pair, more than the bond pair, which in turn repels more than, which is 2 lone pair, which in turn repels more than just that. That's why your bond angle progressively decreases from 109 to 107 there, or 107.5, and then progressively decreasing even further as the lone pair repel and pushes the molecule even further down, giving you 104.5 or 104 degree as that bond angle there, yeah, which is 104. And then we talk a little bit about extra stuff, which might or might not be covered in your chemistry curriculum, but I've seen Sf4 before. It's like a seesaw. Think about that orientation, where we do a linear combination of a linear geometry as well as this band geometry featuring one lone pair, just like I did with trigonal bipyramidal geometry in the previous video. And then there's also this compound called interhalogen molecules. You might have seen this in Olympiad papers or even in AQA extension paper, I guess, like more advanced chemistry stuff. But it's basically counting the lone pair and bond pair, which is a concept you would have been accustomed to. It's just the idea of the lone pair there. You might think that they are best separated by 180 degree, but they are not. Instead, they adopt a T-shaped geometry, which already take into account and optimize optimize the minimization of the repulsion. So VSEPR exists to minimize repulsion. Okay, your lone pair will repel, but this geometry will allow it to minimize the repulsion the most. Okay, and then this square planar geometry of xenon tetrafluoride is quite an unusual one. As a matter of fact, I'd like to add something else. No, I don't want to add something else. No, that's all. Yeah, that's all from me. I'll see you in the next video. And then if you like what I'm doing, if you like my teaching style explanation, please subscribe to the channel, and I'll update the channel with more useful content in the future, hopefully. And please comment on what else you want me to cover, and I'll think about it. And yeah, I'll see you in the next video. Thank you for watching.